Okay. Good morning. First of all, um, hope you all slept well and are ready for the next round of current current electricity. Today we're doing 10.2, but we're going to do 10.2, I think, in two goes, because there is some math involved. Before you start, I want you to get yourself a piece of paper roughly the size of this. This is a card that we're using in Physics 12. Very similar to the stuff that you're going to be doing, believe it or not. Not all this stuff, but this stuff here. So you're going to need either a piece of card stock like this, or at least a piece of paper about this big. And I also, if you have a hole punch, it'd be nice to hole punch it, but if you don't, that's fine. This is your cheat sheet. You're going to be using this when you do any problems. Even on the test, I'm going to have you bring this in. You're also going to need a calculator. Okay, so pause right now and go find yourself a calculator. Maybe you won't need a calculator today, but for the next class you will, and go grab one of these right now. Okay, thank you. Okay, so I could not find a piece of paper for myself. So I'm just taking this piece of paper and I'm going to cut it. Like that. And so here's what it looks like. It's this big. It's a little bigger. It doesn't have to be. Make it a little bit smaller. But that's going to be my cheat sheet. I'm just going to put it out here to the side for now, and we'll get to that maybe in a little bit. Okay? So let's continue on. And so electric current. Part 2. The flow of electrical charges is called electric current. So the flow, you know what? I'm going to drop that. I hate seeing electric charges because that's stupid. The flow of electrons. We do have a name for these, you know. So it's called an electric current. And the word current is a really good thing. It's a good, what would you call it? Good picture word, because it's helpful to think of current in current in a river. They both flow, right? So electric current is the amount of electrons, the amount of electrons that pass a point in a given time. And typically we measure that in seconds. So how many electrons go by in 1 second? So an ampere this is the unit of measurement for current. The unit of measurement measurement. M-E-A-S, thank you. Meant for electrical current is the ampere. Capital A, A-M-P-E-R-E. And we shorten that to just a capital A. The reason it's capitalized is because this is actually a guy's name. And the same as Joule is named after a guy. This one's named after a guy by the name of André Marie Ampere. Now I know what you're thinking. You're thinking, what? This is a guy. I said this is after a guy. And his name is, part of his name is Marie. What's with that? In the olden days, and even in some cultures today, it is not uncommon for males to have part of their name being Marie. And the reason for that is that among Catholic nations, which France and Italy and Spain, at least at one time back in the 1800s, was predominantly Catholic. And the Catholics have this devotion to Mary, and so it was very common for girls to be named Mary for one thing, but it was also common for males to carry the name Maria, Marie, and sometimes even Mary. Okay, so just a sidebar there for you. So some typical examples of current is a light bulb has a current about 1 amp. A toaster jumps up to 13 amps. And you say, whoa, that's a big difference. Well, yeah, I remember we looked at the difference between a light bulb and a heater. Well, toasters, this is a heating appliance, and any heating appliance uses energy like you would not believe. Okay? Whereas a TV, between a toaster and a TV is all the way down to 4 amps, and a car starter, just to get it going, okay, is 500 amps. So when you turn the key and you get that, okay, that little second there is you crank 500 amps. Okay? So, it is said that voltage won't kill you, but current will. So you can build up like 20,000 volts on you and have your hair stand on end if you're hanging on to a Van de Graaff capacitor, but you'll be safe. But the flow of electrons will kill you, will stop your heart. Now, when you touch a source of electricity such that you complete a circuit, you will get an electrical shock, okay? So electricity, or electricity, so that you complete the loop, complete the circuit, you can get an electric shock. So there is a severe electric shock, or the severity depends on the amount of current. Depends on the current. Now before we get started, there is this little conversion thing. So that's the first thing we're going to put on our card here. Grab your card and let's do this. Let's call this the Science 9 Chapter 10 cheat sheet. And 1,000 amps, or 1,000 milliamps, is equal to 1 amp. Okay? Now, one of the things that you're going to be asked to do is to translate between amps and milliamps. The easiest way is to move the decimal point. Decimal point. Okay? So, let's say I have 5 milliamps is equal to how many amps? So I'm going from milliamps to amps. I move decimal left 3 spaces. Okay? So, if the decimal is here, I'm going to move it 3 spaces. 1, 2, 3. And so I'm going to put in a 0. Here's the decimal. 0. So this is now is equal to 0.005 amps. So 5 milliamps is equal to 0.005 amps. What if you're asked to do the other direction? Let's say you're starting with, say, 38, not milliamps, let's say 38 amps, and you're asked how many milliamps is that? Well, you're going to move, here's the decimal point, you're going to move it 3 spaces to the right. So, move decimal right by 3 spaces. So, I'm sorry you couldn't see that. That's one of the things I miss about doing this on in a classroom, is that I don't have anybody to say, hey, Mr. Hayden, I can't see. So we're going to do 3 spaces to the right. Now this is where the decimal is after the 8. So I'm going to do 1, 2, 3. And everywhere I see this, the 0 goes. So 1, 2, 3. So 38 amps is equal to 38,000 milliamps. Okay? Now, right now you may be a bit confused and say, what? What? Don't worry about it. If you've got this is your cheat sheet. You can use this to help figure out the answer to different problems. Okay? So, that aside now, when we're talking about severity of shock, so how bad was the zap? How bad was the zap? Okay? 0.001 amps, or how much milliamps? Well, I'm going to move that 3 spaces, right? To get milliamps, 3 spaces this way. So 1, 2, or 1 milliamp is equal to, you get just a tingling sensation. Tingling sensation. Okay? 0.015 amps, so what I'm going to do, move it 3 spaces to the right. So 1, 2, 3, so 15 milliamps This is when your muscles contract and you can't let go. And that's because your muscles are controlled by electrochemical signals from your brain. Contract. And you can't let go. 1 amp, or how many milliamps? Move 3 spaces to the right. 1, 2, 3, and so a 0 goes there and a 0 goes there, or 1,000 milliamps. The current is potentially lethal. In other words, this can stop your heart. Stop your heart. Okay. How do you feel about that? Okay, not too far to go for today. Okay, let's look at direction of electrical current. Where is it going to? Electrical current from a battery is called DC, and it only goes in one direction. That's why they call it direct current. Okay, so the electric current, to complete this, the electric current from an electric cell, cell or a battery, flows in one direction only. It's called direct current. Or DC. Wall outlets supply alternating current. AC. Okay? This results when the electrons change directions. They're constantly changing directions, as a matter of fact. So that when the electrons constantly reverse directions. In an AC circuit, this is really fast. It's basically 60 times per second. In other words, if I have an electron going this way, he's going to turn around and go back this way, back this way, back this way, back this way. In 1 second, 60 times. Okay? Now, what this means, though, is that even though the electrons go back and forth, for us, it looks like they're going in one direction, but they're not. Okay? They're just going back and forth, back and forth, back and forth. How do you feel about that? I think it's pretty cool. We call this 60 times. We call this 60 hertz. Okay? A hertz is a change in direction in 1 second. Okay? So want to take a quick look at series, what we call series and parallel circuits, and then, yeah, okay, see how far we get. Okay, so series and parallel circuits, this is a big topic. Your buddies in Physics 12 are just finishing. Now, are they finishing? No, they're just going to start this. As a matter of fact, you're ahead of them right now. So devices connected circuits can be connected in series or parallel. In series or in parallel. Okay. In a series circuit, the current goes through each device in sequence. So here we have, here's a picture. I'm going to go in a little bit. Oh, that didn't help. Okay, so here we have a 1.5 volt batteries. I don't know if you knew this or not, but batteries are 1.5 volts. Okay, at least the ones you put in a flashlight are. So this is the bottom end. This is where the electrons come out. So where the electrons come out. So they're going to go in this direction, and they're going to go through this switch. And so the switch, remember, is something that looks like this. Okay, it's going to go around here, and so the electrons are going to go through this one here, go through this light bulb, come out this other side, go through this wire, go through this light bulb, and return back to here. So the electrons are going to go there. Okay, now we can this is the picture again, but we want to diagram it. In this situation here, this is a better diagram. This is another one of those funny things, funny different symbols that are used for lamps, and we said that there is other ones. The one you'll always see me do is always like this. Two curly Q's like that, and a circle around it. And so if I was doing two of them, I would do like this, like that. So these were guys that do a circle here, circle there, and so these guys would be in series. Okay, so here we have, this is kind of interesting because we see the switch. These guys are in series. These guys are in series, but guess what? These guys are in series too. So these are in series. And so the electron's going to go around, because this is the smaller one. This is where the electrons come out. This is the positive. This is where the electrons go back in. Okay? So in a parallel circuit, it's not like that at all. So in a parallel, the current splits. And some of the current goes through each device. Okay, and their little note here is that none of the current goes through both devices. What does that mean? None of the current goes through both devices. I think what that should say is that none of the current will choose to go through one and not the other. Okay, I'm going to rephrase that. None of the current goes through one device and not the other. And it turns out, if both these lamps are the same amount of current will go through each one. Okay, but that's you don't have to worry about that. Okay, so here's again on this side here you see the picture where we have here is the negative end here, so this is where the electrons are going to come out of. They're going to come down here, and at this point here they're going to split up. Part of them are going to go this way, part of them go this way, go through the light bulb, come back out, electrons going this way, same thing here, go this way, and so they'll join up. They'll join up and return to join here and split here. Okay, so it's like it's like if you have one bigger stream and it splits into two smaller streams and then rejoins each other again and goes back to the source. And so here's the diagram of exactly what this is. You have a single cell battery. This is the negative, this is the positive. Electrons come here, split here. Some go through this light or lamp, some go through this lamp. They're rejoined and return to the positive terminal of the battery. Okay, how do you feel about that one? Not so bad, eh? All the mysteries of the universe being explained in simple diagrammatic methodology. Okay, measuring electric current. This is just devices that we use. I think in your text, I'll just throw this up here. I hate it when it gets so shiny like that. That drives me nuts. I don't know how you guys feel about that, but it just absolutely drives me bonkers. Trying to, okay, I'm going to zoom in on that. Sure I am. Okay, so here we have this is an analog, is anything with a needle that goes back and forth. This is digital, and you can see because this has got different contact points that this is a multimeter. So this is called an analog multimeter, but it measures in amps. Okay, so depending on which two of these things. So the red, you always connect one wire to the red, and depending on which one you connect the black wire to and put it in your circuit, it'll give you different readings. Okay, and the trick is to know which one to pick. This one is this is my favorite. This is a digital multimeter, and so it doesn't have a needle. It's digital. You just turn this, and it'll, for basically turning this has the same effect as changing these wires, but this is like so much easier. And this one only gives you 3 possible settings to choose from. This one has got, holy smokes, 1, 2, 3, 4, 5, 6, 7, tons of them. I can't even read them all. Probably about 12 different settings. And not just amps, it'll measure volts, it'll measure resistance, it'll measure a whole bunch of things. And these are like super cool toys to have. Here's another rendition of this. So this has got a dial too, and it has many different scales. But this is a multimeter, but it's an analog multimeter. These are all multimeters. This is an analog multimeter, another analog multimeter, and a digital multimeter. Okay. I'm sorry. This only does amps, so this is only ammeter. These are multi, so they can do more than one thing, like volts and resistance and stuff. But we'll talk about that later. they're just really super cool things to have around. I've got one back in the classroom that I like to play with. It's kind of fun. Anyway, so getting back to the notes, we use an ammeter, and it's AM meter, to measure the amount of current in any point in a circuit. Current at a point in a circuit. And the thing with it is, it has to be part of the circuit, so it has to be actually connected in series, so that you can measure how much is actually going through it. It's going along the path you're checking. So current is the number of electrons flowing past a point in a second. And we talked about that before. Okay, page over. Page 307 of your notes. It says, copy the circuit diagram symbol for an ammeter and copy a circuit diagram of an ammeter in a circuit. So this is what we're talking about here. So you can copy this in. So an ammeter is simply a circle with an A in it, a capital A. Now, this is what we mean when we say it has to be put in series. So the ammeter actually has to be put in a position where all the electrons that are running through the entire circuit go through it. So if the electrons, I don't want to mark this page, but so if the electrons are coming through here, goes through the through the light, we don't have a decrease in the number of electrons moving. It's still the number of electrons moving. The voltage changes, but the number of electrons doesn't. And so as it goes through here, this guy acts like a counter. Like, okay, there's one, there's two, there's three. So this is in series. Okay? And so electrons go back to the positive terminal, and everybody's happy. So that is basically that. Now what I'd like to do is, like right now, I want to continue on with just a little bit of setting up our chart and completing our notes, but I'm going to hold off on I think most of the math until the next day, and I think I want to do 2 math problems with you, and then so you're not going to have any homework today other than drawing those 2 circuit diagrams that I just showed you. Okay? And then the next day we're going to do some really good hardcore math. Alright? So math time. We're on page 7, and we're on page 7, and the first thing that we're going to do is we're going to put 2 equations. I'm going to put this one here, I is equal to Q divided by T. Okay? I this is current. Current is measured in amps, and this is charge. do a different color. Do red. This is charge. And this is measured in something called a coulomb. And it is capital C. And this is T. Time is in seconds. Okay, so let's just finish off these notes. I think this is sufficient. This is really what this is. So electric current is denoted by I, yeah. Unit is amperes, yeah. And that's A, yeah, okay. T is time in seconds, yeah. I get it. This is quantity of electric charge, or electric charge. And this is measured in coulombs, which is capital C. And this, the coulombs are named after Charles. These guys have got great names. They have all these hyphenated names. Charles Augustin de Coulomb, not just Coulomb, de Coulomb. De probably means of a certain place. And so 1 coulomb is equal to the charge of, get this, 6.25 times 10 to the 18 electrons. Now, I don't know if you guys have ever done any scientific notation, but this is the same as saying 6 to 5, and I'm going to go over dot 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 18 zeros, or in this case it's going to be 16 zeros, but 18 decimal points. So this is a very large number. I don't even think that we've got we might have a word for this, but I don't think we do. It'd be something like a atto something, pico, or an atto something. I don't remember the prefixes, and therefore 1 amp is equal to the current of 1 coulomb. That should be capital C. 1 coulomb of charge per second. Okay? All right. I feel better. Got through that. 2 examples. Okay. So what we're going to do, grab your sheet, and what I want to do is I want to put this on my sheet. Now, any time that you can have a single value equal to a ratio, you can make a magic square, not magic square, a magic triangle. And I'm going to make a magic triangle here. And this is the magic triangle. And you can make your own, where I is equal to Q over T. So now you can be asked any question. If you're given any 2 of these, you can solve for the third. For example, suppose you are given charge and time. How do I find current? Current is equal to Q over T. How about if you were given the charge and the current and you're asked to find time? Time is equal to charge divided by current. So T is equal to charge divided by current. And the last one, suppose you're given time and current and you're asked to find the charge. Okay, so Q is equal to I times T. I times T. Pretty sweet, eh? Okay, now that you've got your cheat sheet, let's do a couple of problems. And then I'm going to let you go. We're at 40 minutes right now. We're going to do a couple examples, and then you're free. Free as a bird. I'm going to keep my cheat sheet up here, nice and handy. It says, how many amps of electricity is flowing in a circuit if there's a charge of 150 coulombs in 15 seconds? Now, no matter what grade you're in, if you're in my grade 12 class or in my grade 11, in my grade 10 class or grade 11 class, I always get you to solve problems the same way. This is how you do it. You take your pen or pencil and you circle the different things that you're given and you label them. 150 coulombs. What's that? Identify. This is what? This is charge. This is Q. 15 seconds. This is a measure of time. And it says how many amps. So this is what you're looking for. How many amps is A. And this is the question mark. Or should be due. Amps is measuring current. So in this case, to solve, you say I'm going to use this one here because I've got Q and T. So I is equal to Q divided by T, and that's the first. This is the first step. So this is step one, identify. Second step is to write down the equation. So identify. Second step is equation. Third step is solve. You always do it in that order. So I is equal to Q, 150 coulombs, divided by 15 seconds is equal to, even I can do that in my head, that's equal to 10 amps. Okay? Now, let's do one more, and I'm going to ask you to pause the video, try this, and then come back and we'll check to see how well you did. Pause now. Okay, let's look at it. Again, step one, identify. So, current of 1.2 amps. This is I. Flows through a lamp. How many electrons will go through the lamp in 45 seconds? Now this is a little bit of a sneaky one because in order to do that you have to solve for coulombs, for charge, right? So let's solve for charge. So this is step one. Step two is the equation. Charge is equal to current times time, which is equal to 1.2 amps times 45 seconds. Okay, so I got to get my calculator out. see. Calculator. There. 1.2 times 45 is equal to 54 coulombs. Now, I've got to look back because 1 coulomb, so this is an additional, 1 coulomb is equal to 6.25 times 10 to the 18 electrons. Okay? So, how many electrons? 54 coulombs times 6.25 times 10 to the 18 electrons per coulomb. Now this is where, if you have not used scientific notation before, this will be a wake-up for you. Okay, come on. There you go. So, I'm going to multiply this by this number here. To do that, it's multiply 6.25. You see this EE? Kick the EE, and then you put in 18 equals. And this gives me 3.375. The E means times 10 to the 20th. This part here is the same as E. Okay? And so the number that follows is this guy here. Okay? That's a rather big number. Alright? So you're done for the day. I don't, if you wanted to go ahead and try your luck with different calculations, that's fine. Some of you may feel comfortable enough already, but I'm not expecting you to. My plan for next day is I'm going to go through and I'm going to lead you, have you do it at the same time as me, and then we'll help each other and compare. And then after that, if you're still having problems, I'm going to get you to join me in a Zoom class, and we will hammer at this, because I want you to be so comfortable with these calculations that it'll blow your mom and dad's mind. Like, they just like, wow, you're genius, man. Like, seriously. Okay? Anyway, that's enough for today. Love you. Go away, and I'll see you next day. Don't forget to grab a calculator. If you've got a phone that has a calculator with scientific notation on it, that's fine. But the likelihood is that you'll need one that can do that, okay? Okay, bye now. Love you. Go away.